Heating and electrical power. Consider you have a resistor, current I and resistance R. We all know that voltage, in other words, voltage is the energy per coulomb released. So usually the other units of voltage in joules per coulomb. These are another units of voltage. So usually voltage is the energy released by a coulomb, of electricity that is passed in a conductor. So the energy that is released when this one coulomb is passed is what we call the voltage. Voltage is actually the energy, okay, energy per coulomb released. So if we want to get this energy is equal to the voltage times the charge. So energy is equal to voltage times charge, but we know that charge is equal to current times time, because current is equal to charge power time. So to get this charge, you multiply by time here, you multiply by time here, so you get charge is equal to IT. So finally E is equal to V times IT. So we know that energy is equal to voltage times current times time. So E is equal to VIT, but power we know is energy per time. So when we divide by time throughout, we remain with VI, E divided by time. So we get power is equal to the energy divided by time. So divide by time, we remain with VI. So power is equal to VI. So there are various forms of power. You can convert V, because we know that V is equal to IR. We can substitute V for IR, and we have times IR. So I becomes square times R. Again, we can convert I in terms of V and R. So we know that I is equal to V over R. So if we substitute V over R for I, it becomes V squared divided by R. This is another form. So these are alternative forms, but not you have to be very careful in utilizing these forms. That it is true that dimension wise all these are correct and consistent, but when it comes to application in equations, it becomes a difficult, because you have to be careful what current you're using, because this current you're using might not be this current is here, or this voltage you are speaking here might not be the voltage that is referred there. So you have to be very careful when using this form, but we shall see where and how we apply these forms in the coming examples. So suppose this is the example. So you can see that we usually use this formula to calculate the power dissipated as heat. So usually this specifically to the resistors. So we usually use specifically when we are dealing with resistors. Just a hint. And we usually use this specifically when we are dealing with cells. Okay. We use this when we are dealing with cells. We use this when we are dealing with resistors. Such questions as heat, value dissipated as heat, and etc. etc. So you have to note that you have to be careful in deciding what form you are using, because these values might not necessarily be the same. So for the same that we have known, we can now hereby see the transmission of electrical energy in the national grid. That suppose that power is to be transmitted from a power station to a home or a factory. Since the power is the product of current and voltage, as we have seen earlier, power is the product of current and voltage. Power is the product of current and voltage. A given amount of power can be transmitted either at high voltage or at low and low current, at high voltage and low current, or at low voltage and high current, because this is the product. If you decrease this, you have to increase this to maintain the same power. So the same amount of power can either be transmitted in high voltage low current, or can be transmitted in high current low voltage. And therefore same power can be bound to be wasted by producing heat in the cables as the current flows through them, as I said. the formula of P is equal to I squared R. We usually use this to the resistor. So this is usually to the cell, the power that is transmitted, the power produced has to be transmitted of this value, but this is the amount that will be wasted in the resistors. So kwa haraka tunaweza tukaona the danger of transmitting power with high current. When the current of transmission is high, then the heat produced in the resistors will be high. See, so we have to try to keep our current as low as possible. That's why he proceeds saying, if resistance in the cable is R, the heat energy produced in time t when a current I is flowing through them is IR squared. Yes, just converted into energy. Speaking of power, it's not a deal, it's the same thing. Thus the amount of energy that is wasted is proportional to the square of current in the cables. So if you transmit current in high current, the heat lost on the way is very high. So the most efficient way to transmit power is therefore at high voltage and low current. This is known as high tension transmission. A second advantage of high voltage low current transmission of electrical power is that low currents require thinner and therefore cheaper cables. Why? Because current, the higher the resistance, the smaller the current. So if the current is small, then the resistance can be very high, and we know that the resistance to be very high, one among the ways is for the conductor to be thin, because the smaller the cross-sectional area, the higher the resistance. So the smaller the cross-sectional area, the higher the resistance. But resistance is inverse proportional to current. So the higher the resistance, the lower the current. So if we are transmitting power at low currents, we will require cables that have low cross-sectional area, small cross-sectional area, and that will be an economic advantage. Tutakuwa tunahitaji kutengeneza wires ambazo ni nene au ni kubwa au ni ndefu au ni vitu kama hivyo. So it requires thinner and therefore cheaper cables. A disadvantage is the high cost of substantial insulation needed when employing high voltages. When you are employing high voltages, according to electromagnetism, on the process you will be producing, due to electromagnetic effects, kutakuwa na some current that are produced. So you have to provide sufficient insulators that will avoid any harm anyhow on the way. Kwamba insulator, since these are high voltages, it's very easy for induction to other circuits on the way, na kunakuwa na risk ya short. So the disadvantage ni kwamba high cost of substantial insulation is needed when employing high voltages. In the national grid, for example, in the network cables, which connects Britain's power, Uingereza, to their customers, modern power stations generate alternating current at precise frequency of 50 and about 25 kilovolts. This is stepped up using transformers, easy to produce, to increase this amount of voltages to that range of voltages for efficient transmission, as I've said. So that's the point.